Okay, for the in case of we have similar electronegativity, so as we can see from hydrogen and carbon, they have a sharing the electrons equally, so therefore form non-polar covalent bondings. What if we have then not the hydrogen yet, carbon to, let's say, double bonded oxygen? So what you have to remember here is you don't have to remember the numbers over here. It will not be told in your school exam or whatever. But you can just remember that as carbon has really low electronegativity relatively compared to the oxygen. So thinking about the meaning of the electronegativity here again means that high electronegativity means that tendency of pulling electrons towards itself. So you can think like this is really strong in terms of pulling. So when these are sharing the electrons like this here, carbons almost like taking the oxygen almost like take these electrons towards its side. What that means is, I showed you that before like many times. Inside the carbons, I showed that we have a protons there. These protons will never ever get neutralized by the electrons, fully. In here on the top, when we have the protons there, electrons are equally neutralizing the protons. Can you see that? Now, in case of the electrons orbiting on this side here only, okay, this will neutralize the half value here, this side of here, the surface. But as electron will not go to other side of the electron, the proton, it will never ever get. So this is what I mean by you get the partially positive, because it's not a full positive, but you see the partial charges there. Oxygen side, as almost like it will gain the electron, it will be partially negative. Make sense? Okay. I call this, okay, this is due to the unequal share of the electron. We call this a polar covalent bonding. Now, in case we have a polar covalent bondings like this, okay, Ben, how many polarities do we have in this O and H, or sorry, O and C group? We have two. We have two polarities. One is plus, one is negative. Okay. Instead of we saying the two polarities formed due to that polar covalent bonding every single time, because I can't be bothered to say like a long sentence here, I just simply write that as, hey, we have a two, which is di. We have polarity, take the pole. This is called a dipole. So when we say dipole interaction, that's an interaction between one dipole to another dipole. Okay, so dipole is simply the term that explaining or describing that two polarities due to that non-polar covalent bonding. That's it. Kind of makes sense? Okay. Now, using this then, going back to this CH4, which is called the methane, do you think, I showed you that with the water too. We have a water, oxygen with the hydrogen like this. All right, this oxygen and the hydrogen would have the positive and negative charge because the hydrogen, as we can see, had the really lowest electronegativity among the non-metal groups. Oxygen would have the highest, one of the highest here. So this would be then definitely be partially negative and partially positive. So showing you that the reaction between the another oxygen and hydrogen, which is the water molecule there, because it's a partially positive, partially negative, partially positive, this is partially positive here again too. In between that partial positive and negative of the two water molecules, then yeah, you have to differentiate. We have a 1 and 2 separate molecules. These two will be interacting like this. Okay, so I call this is type of the, hey, that's an interaction between one dipole to another dipole. We call that as dipole-dipole interaction in general. Whenever we have the dipole-dipole interaction means that they have partial charges like this. Does it make sense? Now, the reason why we call this specifically hydrogen bonding is the partial charges of plus and minus from the oxygen and hydrogen is the greatest. Greatest as in like due to that greatest difference between oxygen and hydrogen electronegativity. Make sense? Okay. So it's almost like this. Due to that really great interaction, oxygen is almost like that attached to the hydrogen. Can you say that? Okay. Almost look like what? This is some sort of bonding. Looks like a bonding now, because they're so close to each other. We call this is a hydrogen bonding. So hydrogen bonding is not the bonding between oxygen and hydrogen inside of the water molecules. The hydrogen bonding is actually talking about interaction between the two molecules that are so close together, almost like a bondings. Does it make sense to you? Okay. This is why the water has a relatively high boiling point, because it takes a lot of energy to separate them. Good. Okay. Then, think about the CH4. China, do you think the C and H, what kind of bonding between carbon and hydrogen? Covalent, polar or non-polar? Non-polar. So do you think the water molecules would have a good interaction with the this CH4? No. What's the intermolecular force inside of the for the CH4 then? No, CH4 only has the dispersion force, the weakest, which is kind of common for everything. So there are three types of intermolecular forces: dispersion. We have the dipole-dipole, but dispersion is way less than the dipole-dipole interaction. Hydrogen bonding is part of this. So dipole-dipole is in hydrogen bonding is a type of dipole-dipole, but compared to the strength, hydrogen bonding is strongest, followed by dipole-dipole and dispersion here. Okay. Again, CH4 does not have any polarities, so it cannot have the dipole-dipole or the hydrogen bonding. Hydrogen bonding is only formed when hydrogen forming bonding with oxygen, nitrogen, or fluorine. Okay, again, that's bonding I'm talking about, the in between the molecules. Does it make sense to all? Okay. This has a dispersion force, which is kind of working as non-polar. That dispersion force would not be welcomed by this water. So it means they're not interacting very well. Not much interactions means that solubility of the methane in the water is really poor. So they will not dissolve in the water, just like oil. Okay, oil is made with a lot of carbon and hydrogens, and they do not mix in the water really well because they have a dispersion force from the carbon and hydrogens. Water is full of the hydrogen bonding for intermolecular forces. They are not interacting. So how does it relate to the question over here then? The question 3. Water can wet the cellulose, but it cannot dissolve it. Then, which of the following characteristics of the water or all the cellulose explain this? So, if the cellulose is not dissolved in the water, what tells you then? It's the cellulose. We know the water is a polar. The cellulose is not polar. That's what this tells. So, the answer for what cellulose actually look like this. There's a carb C6H12 and O6. That's the cellulose. It can wet cellulose, but it cannot dissolve it. Yeah, it's kind of hard to know. Cellulose look like this means that there are carbon and oxygen bondings too. So partially there are some of the hydrogen bonding exists there. The answer for the 3 is C. Is hydrogen bonding between the cellulose stands in the strongest, and hydrogen bonding between the water and cellulose. Means that it's bonding between cellulose and cellulose is so strong that water cannot really break the bond between them. The cellulose look like this. There are 6 hydrogen bondings. So in between the cellulose to another cellulose, they are kind of joined really strongly. Whereas water only has 2 hydrogen bonding can form. Okay? 4, okay? If the mercury level is certain variety of the fish is 0.5 or ppm, okay, ppm. What mass of fish of the same variety would have you have to eat to ingest a total of the 100 mercury, mg mercury, okay? Hannah, what's the mercury, what's the ppm? Parts per billion, how to find that? Told you to memorize this because you will get it. Joanne, ppm? Milligrams per liter. That's how we found it. So in terms of grams, that's same as 10 to the power minus 3 grams per liter too. Okay. ppb, parts per billion, would be micrograms per liter in that case. Now, we're given 0.5 ppm. Okay, which is what? The mass of fish is going to get the total 100 milligram there. So the same variety which you have to eat to ingest total. So what we want to get from here, we want to get 100 milligrams. So 0.5 ppm known as 0.5 milligrams per liter of the fish, the volume. To ingest the 100 milligrams, you simply need to divide the 0.5. Okay, then you get half 200, it'll be 2 kilo. It's actually, I'm giving you more, 0.5. So 100 divided by 0.5. You get parts per million, 10 to the power minus, okay, milli, 10 to the power minus 3, minus 6.5. 100 milligram per mercury. Yeah, okay. That should be giving you 100 divided by 200 milligrams, or the liter. And they need to ingest a 200 liter of that fish. That's the same as 200 kg in terms of the unit conversion, and that's same as 2.0 times 10 to the power 5 grams in terms of grams. As the 200 kilogram is the same as the, so you can write that 200 times 10 to the power 3 grams. Okay, so answer is A from the given question here. Five various forces exist between atoms in the molecules and between between molecules, such as, sorry, the question's asking you about intra or inter, Ben? Is the question about inter or intra? Intermolecular forces. So, what are the inter over here? Yep. Between, okay, exist between atoms in the molecules and between the molecules, such as, kind of weird question. I mean, this should be like the 3, the dipole-dipole interaction in that case. Could be the 2, hydrogen bonding, but in the molecules and between. Oh, so guys, don't worry about the question 5. I think this question is missing that. This is actually given. You have to choose something from there. So it's not the answer. It's not actually a question itself. So I think we're missing a question there. 6. Which statement below is equal or to 1 mole of any substance? What is a 1 mole? Joanne, what is a 1 mole? Yep, so it cannot be A. It's 6.022 times 10 to the power 23, not the minus 23, Avogadro's number. Or use your formula sheets. It will be given. It's given on there. Okay. B, the number of the carbon atom in exactly 12 grams of the carbon 12. That's the definition of the moles. So answer is B. That's actually how like Avogadro found out the concept of the moles. Seven, 3 zinc plus 2 iron nitrate produce zinc nitrate and the iron. Which statement best describes the useful information provided by the equations? Okay, thinking about like the coefficient value given over here, 322 to 322, we got to use that. So answer for the question 7, therefore, would be D. That 3 moles of zinc react with 2 moles of iron 3 nitrate. This is the only information that is right. 8. Choose the option that gives the correct example for the terms in italic. Alright, we have a mixture, column 1, and solute and solvent given over here. Okay, to get that right, for the mixture, we can have mud and slurry and wines and that and that. Okay. So thinking about what I mean by solute and solvent. Solute and solvent. Solvent is generally be kind of liquid, or like some sort of like something that mix, can dissolve your solute. So a good example was, I gave you the main example of the sodium chloride, put it into the water. That's a solute, and solvent produce the solution of the sodium chloride, which is salt water. So the only thing that follows that is actually the C. The others, water cannot be the solute. It's just purely just a mixture. Okay, it's not talking about some sort of like a solution forms in here. Same for the mud. Mud could be a various mixture. It's not specifically a solute. Same for the oil and vinegar. Okay. Alright, to the answer question 9 and 10, consider the following properties of water. We have 1 to 5 there. Okay, which of the properties contribute most to the ability of the water to be an agent of the weathering of rocks, both as a liquid and solid? So, agent of the weathering the rocks. For 9, it would be what? From the given over here, it would be the weathering the rocks means that we are kind of like making the rocks into a certain shape. Okay, we can use the water to be both a liquid and solid forms too. So if you ever seen like using the water guns to weathering the rocks, okay, or you're frozen sometimes to making the weathering as well too, like kind of frozen the rocks and kind of cut it. So the answer for that is actually D. It has to expand when frozen, and 5, the interpolar molecules too. It's not an easy question, to be honest, for this. 10. Which of the properties of the water contributes most to the role of the water as a habitat, in which temperature extremes are less than the terrestrial habitats? Don't worry about this one. Question 10. That's an old-fashioned. Answer is B, by the way. It has a high heat, vaporizations, and it expands when frozen. 11. Experts recommend the use of the hot water for more efficient cleaning of the clothes. Okay, this efficiency can be related to the effect of the temperature on the surface tension and the viscosity of the water. Which of the statements correctly describes the effect of the increase in temperature on the intermolecular forces in water? Okay, so intermolecular forces water, the temperature. What happened to the interaction between water molecules as we kind of increase the heat? So thinking about 0, 25, and 100 degrees Celsius, okay, they will like giving more heat means that they start to be expand, start more like separated. So in terms of that, the intermolecular force must be decreased. So it cannot be answer C or D. It's just be decreased in the intermolecular force. Now you remember about interaction. Interaction is getting weakened. Now that means that viscosity, as you increase the temperature, the viscosity also gets decreased too. So it's either B, it's A is the answer. So this is something that's useful to remember, that the high boiling point, we increase the heat means that we increase the distance between the molecules. It will kind of decrease all the physical properties, including the viscosity and surface tension. Make sense? 12. Concentration of the substances in the mixtures are normally expressed according to the amount of substance in the mixture and the weather. It is used in the commerce, the home, or the laboratory. Choose the units used for expressing the concentration of the substances listed. Okay, so what we actually use to measuring the mercury in the oyster, we generally use the ppm. Okay, so it's that's not 1. So is that A or C? Let's say that salt in cookies. Have you ever seen like salt content in cookies in ppm? It's actually quite a lot of salt in the cookies, more than you'd imagine. So you can't use ppm for that. So it'll be C, percentage of weight per weight. We'll say like, oh, there's a 0.1% of salt. Sugar would be 20% of salt, sugar. All right, 13. Consider the solubility curve for the various substances shown in the diagram. Which of the salt has the highest solubility at 27? Now, salt in here is talking about ionic compound. It's not just sodium chloride. This means ionic compound. So we have a various ionic compounds given on the graph over here. So at 27, guys, this is what you need to do. Grab your ruler. Where's my ruler? Here. Grab your ruler, point at 27 in your graph, which is somewhere in here. That's 27. Draw a line, okay, and see where you get the highest point. So you will see that, oh, at the 27, it's not straight enough. So make it straight. 27 is a proxy here. That's 27. Okay, that's the point that we get the highest solubility. So it's either be like a sodium nitrate or a calcium chloride here. But if you just use the data correctly, I kind of limited because of the blurry data here. You should get the C, which the calcium chloride has slightly higher solubility than sodium nitrate. That's what you can do. This is part of the working scientifically skills. 14. How many oxygen atoms are present in 10 grams of magnesium nitrate? Okay, we have a 10 grams of magnesium nitrate, means we have Mg nitrate is NO3. So we have a Mg, NO3, N2. Start from here. Okay, and once we get it up to here, we know the mass of the Mg NO3 is given at 10.0 grams. What we need to do, find the number of moles. So, and what we know about MgNO3 per magnesium nitrate, per magnesium nitrate, how many oxygen atoms do we have? There are six oxygen. Okay, so if you can find the number mole of this by m over molar mass, that's given at 10 divided by certain values. Use your periodic table again here. So Mg 24.31 plus that 2 times 2, 14.01 plus 6, 16. You get number of mole of this magnesium nitrate first of all. You get 0.0674 mole. That means N of the oxygen would be times 6 of that value. So times 6 that, you get 0.4045 mole, given up to here. Question asks you to find the oxygen atom, how many? So what we need to do to find the oxygen, 0.4045 times Avogadro's number. That's 6.022 times 10 to the power 23. So times that. You would get 2.4 times 10 to the power 23. So the answer is B. Now, for in the exam, for the multiple choice, you only have a 1 minute. 1 minute to 1.5. That means you do not need to provide these kind of working out. If that helps you to answer better, or if you want to check the answer later on, yes, I recommend you write a kind of brief, rough working out in your multiple choice over here. Otherwise, if you knew how to do this question, how to approach to the question, use your calculator. Okay, just play with the calculator, get the value early, and try to check it again. All right, 15. Which of the following occupies the greatest volume at 25 degrees Celsius? So it means, okay, we have 1 mole of sulfur dioxide gas, 64 grams is the oxygen gas, 53 liters is given the volume. We have 1.8 times 10 to the power 24 of molecules of hydrogen gas. So for individual of that, except the question 3 C, the answer C is given the volume. You can find the volume of the gas using what? The molar volume at SLC, which is 24.79. So given that 1 mole, that's straight giving us 24.79 liter straight away. Okay, having 64 grams of oxygen gas, so you can just simply find the number of moles. So 64 is the number of the grams divided by oxygen is 32, gas is 32, so you get 2 moles. So giving you that 2 times 24.79, roughly about 50. Roughly 50. Now, last one is kind of tricky. It looks like, oh, we have 1.8. So started from the Avogadro's number then. 1.8 times 10 to the power of 24 divided by 6.0 and 10 to the power of 23. You get 2.989. So that's giving you almost like 3 moles. Aha. Having 3 moles compared to the 25, the 3 times 24.79 would give you 74. So 75, roughly, liter. So the answer is D. Again, you have to master those, like all the finding number mole formulas, N equals to M over MM, or molar volumes too. Okay, 16. Consider the 3 substances, ammonia, water, and hydrogen sulfide. A. Construct the Lewis electron dot structures for the 3 compounds. We have ammonia and water and hydrogen. Okay, ammonia is look like this, N of the lone pair on the top, and 3 hydrogens. Forming like this. This is how the ammonia. Okay, water will be like there's 2 lone pair on the top, and this is shown, or O and X doesn't really matter. Sulfur, hydrogen sulfide would be just 1 sulfur with the 2 hydrogens with the lone pair on the top here. Oh, here like this. That's hydrogen sulfide. Now, Vesper theory. Vesper theory. I know you hate it. Okay. Today I will make it really, really easy for you. Okay. You just need to memorize a few things in here. So the rule for the Vesper theory is number 1 is you count the how many things are attached to the central atom. So for example, in here, you see that nitrogen, that's your central atom. So how many things are attached? We can see like there's 1, 2, 3 hydrogens attached with the 1 lone pair on the top. So there are in total 4. So there's 4 things. I'll just say the things in here. What about oxygen, Ben? There will be 4. We have 1, 2, 3, and 4. There's 4 things here again. This one also be 1, 2, 3, and 4. There's 4 things attached to here. Okay? Kind of makes sense. Okay, everyone okay with that? I need to find one more. No, let's do it up to here for now. Okay, and then what you do is you find the base structure. Oh, I'll give you one more. The carbon with the oxygen here. The carbon dioxide there. So for the carbon dioxide, this is a central atom. Hannah, how many things attached to the carbon? 4? I mean, I can only see that 2 oxygens attached. There's no lone pair. When you're having a double bond, we just kind of consider it as one single. I just want to count that how many things are attached, regardless of the bonding state. So there are 2 things attached over here. Kind of makes sense, actually. Then the base structures would have, when you have 2 things attached, this will be a linear shape. Will be your base structure. When you have 3 things attached, okay, that'll be a trigonal trigonoplanar. Do you remember the trigonoplanar shape? Okay. When you have four things attached, this is a tetrahedral. So that's your, I call it the base pair here, base structure here. Then you count the any lone pair. So I show you what it means in here. So I give you this tetrahedral shape over here. This is a tetrahedral shape. As you can see that the carbon with the four hydrogen is known as tetrahedral shape. So you can see the angle between each of them is known as 109 degrees. You don't need to know the angles for year 11 here. You just need to know this is a tetrahedral. That's all you need to know. Now, we have one for the nitrogen here. We have about four things attached. So the base would be tetrahedral, yeah? Now, as we have one lone pair on the top, it simply means that we don't really have the hydrogen on the top. So I do this. That's your shape. We have a lone pair on the top with a 3. What's the shape look like? The shape is known as trigonal pyramidal. Yep, because it looks like a pyramid with the 3. This is how you count the best pair theory. Easy, okay? Rather than you memorizing all that, this is how we chased up. What about four things attached in here? Again, we have water. The oxygen in central atom has four things attached. The base would be a tetrahedral, but with the two lone pairs. Can you see that? With the two lone pairs here. So what I do, I remove that two pairs. 1 and 2. What's this shape? It's a bent. We get the bent shape straight away from here. This is how you can get the bent shape. Okay, same things for these four things, tetrahedral, and then this will be also the bent in the same reason why. Now what about this one? We have a carbon with the two oxygens attached. So two things attached in here. Get two things attached. We don't have a lone pair. So the shape would be linear due to that. That's all you need to remember to get the Vesper theory right. Okay, so even for the PCl5 or PCl4, PCl3, okay, let's go for the PCl3 then. I'm not going to go to PCl5, PCl3. What would be then structure of the PCl3? China, what would be the structure of PCl3? Sure. Phosphorus, P has how many? So started from the number of the valence electron. Phosphorus has 5 valence electrons. It's a group 15. You can use a periodic table if you're not too certain about it. So there are 5 valence electrons like this. Okay, and 3 chlorines means we have 3 chlorines attached over here. Now, how many things attached? 4. So base shape must be tetrahedral again. How many lone pair do we have? We have 1. So it'll be trigonal pyramidal. The shape again too. Easy to do this by doing this, okay? Let's do one more. Okay, what about this one? CCl4 and HCN. Ben, what would be the shape of the CCl4? Square planar? Yeah, we have a carbon, start from Lewis structure here again. So we have a carbon in the center here, okay? Carbon can form up to 4 covalent bonding. So you can form it Cl, 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 and Cl there. How many things attached to carbon? 4. So what's the base shape? What's the base shape? Tetrahedral. Do we have any lone pair? No, so it'll be a tetrahedral. Yeah, That's how you do it. What about HCN? Oh, give it a go. HCN. Try it. I'll give you one more. There's one more. What was that? I did that last time. Oh, and do this one too. NO2 plus. That's known as the sulfite. Purity table. Yep. Here, plus one. HCN, so started from the carbon, which is your central atom. Okay, nitrogen, just remember, nitrogen can form up to 3 covalent bondings. So with the CN, cyanide, we form 3 no covalent bonding with the nitrogen like this. Okay, hydrogen can form up to 1 covalent bonding. So with the hydrogen goes up here like that. So time to see what we have. We have a central atom here, which is carbon. How many things attached, Joanne, to the carbon? There are 2, regardless of the bondings here. We only have 2 things attached. What's the base of the base structure of 2 things? It's a linear. Now, do we have any lone pair on the carbon? So it's a linear shape. Okay, next one, NO2. Again, nitrogen can form up to 3 covalent bondings. So having plus charge means what? Being ionic means plus charge means they lost 1 electron. So instead of forming that, they're actually forming single bonds to each with the oxygen. And one of the bonding is missing, like this. Because due to that, they're forming ionic bonding here. So, but charge on here, it doesn't really matter. It's not really defining the shape here yet. Any lone pair? Yes, you would have that 1 lone pair on the top. Okay. Hannah, how many things attached to this 3? There's a 1, 2, and 3. Now, what's the base of the 3 things? Base of 3 things. It's a trigonal. It's trigonal planar. It's a 3 things. Now we have a 1 lone pair. So 3 things as in like on the base we have something like this. This is the kind of trigonal planar. Okay. We don't have 1 lone pair on the top. What's this shape? Bent. This is a bent shape. Trigonal planar looks like this, Joanne. That's a trigonal planar. Plane. It's a pyramidal. It's like a pyramidal. Plane. Planar means plane. Like a surface, the plane goes up like here. We don't have 1 thing due to the lone pair, making what? Bent shape. Easy? Yeah? So Lewis structures are very important and just need to consider about how many things attached. We don't do the octahedral yet, or like something octahedral is not part of the year 11 syllabus, to be honest. But this is the question that you will get in your half-yearly form. Like, I'll show you 100%. So using that, identify the molecular shape of the ammonia. Again, ammonia is, you can identify that as a trigonal. Yeah. You can memorize some shapes of the very useful, or some like shape of the ammonia and water, because they're known for that. But you can use that rules again. You can use this method all the times. Easy for the best part. Okay. C. Discuss the intermolecular forces that explain the melting and boiling points of the three substances. Okay, so what about the inter? So again, ammonia will look like this with the lone pair OH. It's not a dot structure. I'm just showing you that sulfur. It's band shape here again. So what are the intermolecular forces for the nitrogen and hydrogen? So we can start out here like two. The strength, the melting point, melting and boiling point of the substances points are depend on their intermolecular force strengths. Okay, so greater the intermolecular force means greater the higher the boiling point, the higher the melting point. So what's the intermolecular force for nitrogen, hydrogen, ammonia? What would be interaction between this ammonia to another ammonia? It'll be hydrogen bonding because it's the bonding between hydrogen and nitrogen. What about water? That'll also be hydrogen bonding. What about the sulfur, this hydrogen sulfide? It would be the dipole-dipole. Okay, so the strength would be the greatest for the water because oxygen carries the greater electronegativity than nitrogen. Think about the trends in your periodic tables. Yeah, so we expect that water would have the slightly higher the boiling point than ammonia due to that greater intermolecular forces. Okay, and the lowest for the sulfur dioxide here. That's what you need to say. Okay, you can also talk about some of the dispersion force. The way we can increase the dispersion force is we attach to something heavier non-metals. So comparing the molar mass of this sulfur dioxide to that, this is actually heavy. So compared to other two, this will carry some greater dispersion force. But that dispersion force, as we know, is the weakest among that intermolecular forces. Would not be could be negligible in this case, but still be giving a little higher the boiling point than others. Make sense? Did I give you the printed answer for this one last week? Yeah, so have a look at the sample answer given on here. It's very useful to make your own answer. Okay, let's do after question 17, have a short break after this. 0.534 grams of the calcium chloride was dissolved in the enough water to make 500 ml of solution. So unit conversion for this, we need to find that in ppm, calcium in ppm. So ppm again stands for milligrams per liter. Okay, that can be found by the milligrams, which is 0.534 grams into milligrams, can be found by times 10 to the power minus 3, 10 to the power 3, I'm sorry. For the milligrams, divided by the liter, which is 0.5 liter there. That's a milligram. Grams on 500 milliliter. I'll write that. Okay, can you see I just simply got converting unit from milliliter to liter, grams to milligrams. Okay, put that in your calculator, then you'll get 1,680 ppm. But what's sig fix? What's sig fix? It's given as 500. That's a 4 sig fix. 3 sig fix here. As you're dividing 3 sig fix by 4 sig fix, you need to follow the lowest sig fix in this case. So the answer, even though the answer is 1068 given, that's a 4 sig fix values, your answer should be 1070 for the 3 sig fix. But I had a question from some other classes. Isn't that a 4? That could be a 4 sig fix as well too. So the safest way to show the 3 sig fix is you write it like this: 1.07 times 10 to the power of 123. That's surely showing the 3 sigma value of the ppm. Okay. 2 in the mole per liter. To find the mole per liter, so we get the concentration. That's calcium. N equals to, so we know N equals to molar, m over molar mass. So N equals to m over molar mass. And what we know about the concentration is N over V. So yes, you can find the number of moles and concentration separately, or you can combine these two together. Okay, by combining these, then as N is m over m over molar mass, we can write the m over molar mass for the number of moles times 1 over V. That's what you can do as well too. Okay, then you'll get mass is 0.534 for the calcium divided by the molar mass of the calcium. The calcium chloride. Oh yeah, calcium chloride would be the 40.08 plus that to 2 times 35.45 for chloride. That times the 1 over volume, which is 1 over 0.5 here again. Okay, then you'll get 9.62 times 10 to the power of minus 3 molar, or mole per liter. You should write the mole per liter in your answer. Yep. B, what is the concentration of chloride ions? Chloride ions in percentage weight per volume. So what's the weight per volume, Songbin? Weight per volume. Percentage weight per volume. How do you find the weight per volume? It'll be the grams per liter. We have to find the grams per liter. So to find that, we're going to use the one we have on the top. So this is not a calcium ion, sorry. That's the same as calcium chloride, first of all. Okay. If we know the concentration of calcium chloride is this, okay, can we say then the concentration of the chloride ion itself, from here, we think about like how many chloride we have. We have per calcium chloride, we have 2 chloride in it. Means if the calcium chloride concentration is this, the chloride, just chloride concentration would be times 2 of that value. Does it make sense? Does it make sense though? This is a very important part because we got to use that again in year 12, module 5, 6, 7. If we have a concentration, okay, just think about we have a one calcium chloride. Okay, then how many chloride do we have? We have 2 chloride ions in there. If I have 1 mole of calcium chloride, that would be 2 moles of chloride. Everyone good up to here. Now what I'm doing here is, if I have concentration 1 mole per liter calcium chloride, which means that in the 1 liter, we have a 1 mole. That means if I have a 1 liter and 1 mole, in the same liter, I would have a 2 mole per liter of the chloride ion too, because the quantity, the number of the chloride ions would not be varied unless you added more of those or extract more out. So this is why we can make an assumption that if the concentration of calcium chloride is this, okay, the chloride concentration would be 2 times the concentration of calcium chloride over here. Or if you're not too certain, you can find that number of moles and divide that with the volume of the 0.5 again too, but you get the same answer basically. Then this is known as that 9.62 times that, so it'll be the CV and that. You know, I just leave that for like just leave that, or just 2 times 9.62 times 10 to the power minus 3 mole per liter is the chloride concentration first of all. From here, we can find it's a 500 mils given. It's 500 mils. So we can find the N of the Cl minus. Okay. Oh, let's go for like here. So if I want to get the mass of Cl minus given here straight away, okay, or the concentration in the gram per liter, if I want to get that, as we have a concentration in mole per liter, converting mole to the grams, converting mole from mole to grams, we need to, that's N, to M. We know the M is equal to N times the molar mass. Okay, so if you want to convert the unit from mole per liter to gram per liter, you simply need to times that molar mass of the chloride. So it'll be what? 2 times 9.62 times 10 to the power minus 3. That times that molar mass of the chloride, which is 35.45. That will give you that 0.341 gram per liter. First of all, it will give you this. Okay. From here, to find that gram per liter concentration, 0.0, that's given as gram per liter. So in 1,000 milliliters. So actually, it's the percentage by weight per volume is gram per milliliter times 100%. It's not the liter form. So to convert that into it, this is the same as 0.0341 or 341 grams on 1,000 milliliter, isn't it? Because 1 liter is the same as 1,000 milliliter. Then it will give you that 0.0341% in weight per volume. Make sure you write that, the weight per volume, in your final answer. This is the answer for this question B. Everyone good? Okay. Guys, playing with those, the conversion, unit conversion, you will get these, at least one unit conversion. And this is not the end of the unit conversion, by the way. In year 12, you actually get the unit conversion in module 8, which is like next year. Next year, like June or July. So by the time you forget about all the things, ppm, percentage weight per volume, because we don't really come back to this until we do that part. But HSC started giving you these kind of questions again. They're like, hey, what's the concentration of weight per volume? And everyone's like, oh my God, I forgot that. I learned that in module 2, but I forgot that. It was last year. So that's illegal, giving me that question. Yeah, actually they said it's illegal giving me the year 11 question for year 12. I'm like, dude, you still get the plus and minus in the math. Do you think that's illegal? Yeah. Do you still get multiplication? You still know how to do those differentiations in year 12. That's not illegal. Okay. All right. Have a short break. Yes. Which one? Here. Are you sure? 0.3 on 4? No? 9.6. Oh, the answer might be wrong then. Yeah, you're right. The answer's wrong. Times 2 times 35.45. Oh, fix that. Okay. Oh, so you should get 0.68. 682 gram per liter. That means it would change the whole answer. That would be 0.682, so 0.0682% there. Yeah, you're right. Well done. All right, any questions? Let's have a break.
Still can't believe it's like 10 a.m.
Okay, question 2678. You don't have the answers to the answer I gave you last week. Yeah, you don't have the actual answer. So I go through some of the answers for those together now. So 5 consecutive elements in increasing the atomic number have first ionization energies, as shown in the table below. So we are given W to Z, but just quickly revising that, what do you mean by the first ionization energy? Joanne, what do you mean by the first ionization energy?
Energy required to remove electron.
There we go. So having the greater greater ionizing energy means that, do you think that would be more on metal side or non-metal side? Having more of the greater ionizing energy. So if it takes a lot of energy to remove the electron from the valence shell, which means that they have a lot of valence electrons available basically. So it's hard to remove from that conditions we have. So in case we have W, V, X, Y, and Z, you see that V has the highest ionizing energy, which means it's most likely to be a non-metal sections, and whereas X is like less than that. It's actually saying like 1,000 smaller than what we had before in here. So it most likely be a metal sections there. This is something you can think before you attempt the question over here. So using that, define the first ion energy. As you said, the energy required to remove the first valence electron. The first, this is very important. That's how you define it. B, identify which element W to Z would be most likely to be a noble gases. So among that group over here, noble gases would be the highest first ionizing energy. So therefore, it would be the V. It would be the most likely noble gas. 2, from the ion with the 1+ charge. To have a 1+ charge, it needs to lose one valence electron, like a metals in group 1. So question asking you, what would be the chance of having a group 1 among that group? So it'll be X that has the lowest ionizing energy in that case. B, metal, so it'll be either be X, Y, and Z, because all of them have the relatively low ionization energy compared to W or V. Exists as a diatomic molecules. Okay, comes out diatomic. Diatomic means that they will come out in the forms of the two molecules joined by covalent bondings. So as we take the V as a noble gas, most likely be a W would be your diatomic form. So it could be a chlorine, halogens, chlorine, fluorine, or bromine in that case, forming Br2, Cl2, or the F2. 5, react most vigorously with the dilute hydrochloric acid. So something that reacted with the hydrochloric acid is known as the metals. The most reactive metal will react with the strong acids vigorously, really strongly. So in that case, would it be X, the most reactive metal in that case? Next one, 27. Explain why atomic radii decreases as you move along the period of the periodic table, but increase as you move down a group. So again, kind of easy questions because I explained you that. Actually, ask you to memorize the explanations. Going down a group, what happened is as the atomic radius gets increased due to the increased number of the shells, due to the number of shells, what happens? Atomic radius gets increase due to that reason. Now, across the period, the atomic radii gets decreased as the number of the protons in the nucleus get increased. There will be greater electrostatic force of attraction towards the nucleus, which makes it shrink the radii sizes. Yes? It'll be describing like why this is that, 4 marker. So 2 marks for the explaining decrease along the period and increase down a group. So 2 marks for each to that. What'd you get? 3? 2. Okay, I'll check that again. Is anyone got like 2 or 3? 2? I'll check that again too. All right. But explanation for every other the trends will be similar or the same. Now 28, well, this is something that might confuse you. Now chromium is often found in the in the Earth's crust as a chromite, FeCr2O4. The production of the chromium metal from the chromite involves a series of the chemical reactions. We have the chemical reaction going. So what you have to understand from these multiple chemical reactions is we started from the iron chromate, so as this is given, okay, and to produce that chromium at the end. That's what we want to get. So A 210 grams ore sample containing 75.4% of chromite by mass is processed through this series of the chemical reactions. So calculate the mass of the iron chromate presented in 210. So for that, as we have the percentage of the iron chromate, it's given as 75.4%. Okay, if we have a 210, so the mass of the iron chromate would be from the total mass times 0.7540 of this. So you get 210 times 0.7540. You get 158 times 0.34 grams. Now, what you probably get is you have 4 sig figs. There are 4 sig figs, so you need to change your answer to a 4 sig fig value. That's approximately 158.3 grams in 4 sig figs. That's the answer for A. Good. B. Calculate the mass of the carbon dioxide gas produced when chromium is produced when the 210 gram ore sampled by this process. So we need to find the carbon dioxide gas over here, the mass of that. So what we know about here is we got to give it a mass of this, so the iron chromate. So N of the iron chromate can be found by M of a molar mass. Make sure you show the working out here. That's 158.3 divided by, adding up all that relative, the values we have. So iron is 55.85 plus 2 chromate Cr 52 plus 4 oxygens like this. Okay, if you found it correctly, then 55.85 plus 2 times 52 plus 4 times 16 and 158.3 divided by that value, you get 0.7071. But here's my tip. If you want to find the exact values, okay, I recommend you to leave your answer in the form of the fraction like this first. So that's 223.85 there. Rather you find some values over here, because if you find the value and put it into another formula or the equations, there could be a sig fig error. So you probably see that sometimes you get a different answer to the answer sheet because that's due to that sig fig. So this is my recommendation, to leave that number over here. That's giving the same as a mole. Okay, and as we can use the molar ratio, the Fe, the iron chromate to the carbon dioxide, we can use this. Then we can use that as the N of CO2 would be 2 times of the FeCr2O4, okay, according to the reaction ratio of that, which is of 1 to 2, or 4 to 8, the same as 1 to 2. So this is what? 2 times of that, so you can show that 2 times 158.3 on 2 to 3.85. Leave that for here yet, as we need to find the mass. Therefore, mass of the CO2 is known as what? N times the molar mass. Show that 2 times 158.3 divided by 2 to 3.85 times the molar mass of carbon dioxide, which is 12.01 plus 2 times 16 for the carbon dioxide. So do that now, then you would get times 2 and you get 62. Again, we fix that into the sig fig. We have a 4 sig fig given, so it's 4 sig fig and 2 sig fig, so it could be a 4 sig figs. 4 sig fig would be 62.25 grams for the carbon dioxide produced. All right. C. Calculate the mass of the chromium metals produced by this process using the 210 grams. Chromium metals produced by this in this process. Okay, chromium metals, which is given over here. So we need to find that. So will be some sort of the reaction ratio game from here. So what we have to see there is for the 4 moles of the iron 2, okay, that's producing 8. Can you see that from 4 to 8? Okay, and that 2, from the 2 produce this Na2Cr2O7. That's given on over here again, and per that, which produced the Cr2O3. The Cr2O3 is used to get that. So we're going to play around with some molar ratio in here, first of all. So let's write it down. N of the, what we have, Fe2. Fe, I'm going to rewrite that on the top. So what we are given, N of the FeCr2O4 is given as, we found that as approximately 2 times 158.3 divided by 223.85 mole. You can find the approximate value if you like to. Okay. So let's use the reaction ratio first of all here. Okay. If it's given that, N of the Na2CrO, using the first equation from the equation 1, is 1 to 2. Okay, so 1 to 2, it would be same as 2 times N of the FeCr2O4. That's equation 1. Make sense up to here? Then, for the equation 2 here, Na2CrO4, as you can see, this is related. Then, we need to find the concentration, the next one. The number mole of the Na2Cr2O7, using the reaction ratio of that here, is 1:2. So, what you can tell is the half of the N of the Na2CrO like here. Can you see that? Okay. Now, can I just replace that with this one here? Can I substitute this one to here? 1 to 2. Then you would get that same as half times N of the Na2. That's actually same as the 2 times that. That's same half times that, so you get the N of the FeCr2O4 here again. Does it make sense? Okay, good up to here. So make the equation 2. Or we can show that that's equation 2. Show the substitution of 1 to 2. Then you get the equation 3 like this. Good up to here. We do the same thing in here. Next one. To get the chromate concentrate number moles, N of the Cr2O3 would be same as what? Using the following reaction ratio. That's actually same as a number mole of the Na2Cr2O7 from the third equation here. Okay, then this is what? Same as N of the FeCr2O4. The same as that. Equation 4. Next one. We now have Cr2O3 is same as this. So find the number mole of this Cr itself. That's what? 2 times of the Cr2O3, which is what? Substituting the Cr2O3, that's same as this. That's same as 2 times N of the FeCr2O4. Okay, so it looks complicated, but I'm just playing around with some reaction ratio here again. This is what we get. This is the same as what? We found that N is given off the top, so 2 times 158.3 divided by 223.85. Yep, so 2 times 108.3 divided by 223.85. I know, did you get 1.414 mole? Okay, are we done? Are we done? No, we need to find the mass from here. We need to find the mass. Mass is easy. Mass of the chromium, therefore, is simply N times molar mass. Okay, the chromium is given on your periodic table again. So Cr, which is known as 52. So 1.414 times 52, you get the grams of the chromium times 52. You get 73.54. So in the given sig figs, again, 4 sig figs, leave down this grams here. That's the final answer. Looks complicated, but it's if that makes sense, if that sounds reasonable, yep, that's how you need to do it, playing around with this. The last one, calculate the number of the aluminium atoms consumed in this aluminium atom. The question's asking you the number of the aluminium atoms. So you need to use Avogadro's number for this. Aluminium, where is aluminium over here? It's given over here. Yep, so to get the aluminium, the N aluminium then, for question D, N of the aluminium, for the reaction ratio, the chromate is the same as what? This is 2 times of the N of the chromium, Cr2O, Cr2O3, according to reaction ratio here again too. What is this 2N this? That's same as 1.414. We found it from question C. Can you see that? Okay, you say 1.414. Or you can show that the same as 2N of the FeCr2O4 from the previous question. How to find the number of the aluminium? 1.414 times 6.022 times 10 to the power 23. So 1.414 times 6.022 times 10 to the power 23. You're to get 8.51. 515 times 10 to the power 23 atoms are required. Guys, this is relatively 7-marker question. Okay, so I know it's relatively harder than the other questions you've tried before because we have multiple chemical reactions given. So you get frightened by looking, oh, why so many reactions here? And you're like, oh, I don't want to do this. I will skip it. And guess what? You're skipping the 7-marker questions. This paper is out of 80. If you skip 7-marker from there, you will never get to 80%. So you need to challenge it, you need to push it. The hardest question could be this. I'm not giving you, if I'm making a question really hard, this is actually HSC styles these days, you won't get A, B, C, D in the end questions. Instead, you will be asked to find, hey, find me the grams of the chromium straight away, 7-marker, bam. Without the step-by-step A, B, C, D. That's the current HSC trend. That's what I mean by, oh, you get harder questions. Because you need to think, you need to understand the question, you need to comprehend, you need to utilize that. That's hard, that requires a lot of practice, by the way. Okay, so this is the kind of process like we're preparing that. We're getting there. We're getting there. Any questions about the paper? Anything you want to ask? Yes?
Question
25. Don't worry about the first question, the ionic equation. You haven't learned that yet. But quickly just explaining you what I mean by the ionic equation is. The ionic, so I show the 2 equations over here, the full equation and ionic equation. So when we write, say, the full equation, we kind of did that in year 10 before, but let's come back to this. We have a sodium chloride in the water, so we have sodium chloride, the aqueous solid, is mixed with the water, H2O liquid, okay, or forms of that, and forming the sodium and chloride solution. That's what I mean by showing the equation here. But thinking about the ionic equations, we exclude the water, showing the solvent. We simply show that sodium chloride underwent the reaction of the dissolution, forms this. That's just simply known as the ionic equations. It could be actually go the double errors because they can form back to sodium chloride too. Okay, so from you will see that there are some okay. The way we can determine the chemical reaction is we look for this any chemical the state changes here. We've seen that from sodium chloride, okay, from the ionic bondings to some of the bondings over here like this. Now, question B. It's kind of popular question still in the HSC as well too. So how we show these solutions. So for example, first of all, you show the sodium chloride on here. This is my way to show that chloride over here. Ben, what's the bonding between sodium and chloride again? Ionic. So you need to show that there's ionic bondings. Okay. Now, what happens is if that goes through the reaction with the water comes along like this. They're not really interacting yet. So water has partial positive, partial negative, partial positive charges like this. You see that? Okay. Now this is kind of going along. You have to think about interaction here. In the ionic bonding, or in the ions, they are having plus and minuses. Okay, sodium plus, chloride minus. In the water, they have some partial charges of plus and minus. So the important thing is they're partial, means they're not complete one. So what they do is this minus will be attracted towards the positive charge over here. This plus will be attracted to the negative there. So what happens is it will kind of separate the ion. It will kind of breaking down the ionic bonding, separate the sodium ions and chloride ions like this. There will be water molecules comes along. So sodium ion will be surrounded by oxygen heads, multiple oxygen heads like this. And chloride ion will be surrounded by the hydrogen tails of the water. Like that. Due to what? There's a partial charges, partial positive of the hydrogens, and the partial negative of the oxygens. So you'll see there are interaction of the partial charges there. Can you see that? The partial charges will be interacting each other. Now this charge, this interaction here, we name that as this. This is the interaction we name that as this is the interaction between an ion to the dipole. Yep, you get the meaning of the dipole now. Okay, ion and dipole. This is known as ion dipole interaction. What a name. This is how we name it. Very easy to name it. Once you know what we mean by ions and dipole, this is how we name the interaction. Okay, it's a part of the solubility that we'll learn again in part of the module 3, a little bit of module 3, and lots of the module 5 in year 12. Any questions to draw that? You get the very similar diagrams in your answer given. So when do you think, this is part of the module 3 again, when do you think the sodium chloride, why do you think the sodium chloride would dissolve in water?
Because sodium chloride is positive and negative.
Yeah, so in case we have something dissolved from the ionic, means the ionic bonding strength, think about strength over here, you're holding hands each other. If someone helps you to detach the hand, there's a breaking bond of ionic bondings, which means that the ion dipole interaction between water molecules to these ions are greater than ionic bonding strengths. So this water has a kind of greater interaction than ionic bonding between sodium and chloride. Does it make sense? Okay. Which means that you also have some precipitate, some of the ionic compounds that do not dissolve in the water. Like for example, silver chloride, white precipitate. Which means silver and chloride holding hands really tightly like this. So even water comes along, they would not able to take this part away. That's the formation of the precipitate. Okay? This is part of bit of module 3 and module 5 in year 11 and 12. But we actually had that question in HSC too. Same question in HSC before. Any questions? Easy? Okay.